My dear viewers, I am before you with the sixth part of Physics Class 12, the Chapter 1. Uh, Now I am going to make you understand this torque on a dipole placed in a uniform electric field. First of all, how can we prepare an electric field? Electric field, just these are the field lines, no? These lines are the field lines. So there will be a source over here, positive charge. From that, these lines emanate and then will meet at the negative point somewhere. Okay, in that field, when this field is created by a positive charge, the field lines will go and end in a negative charge. In that bit, within that field, within that field, when we place a dipole, look at this diagram. This is the positive charge. This is the negative charge. So A and B. A is negative, B is positive. So we can write the plus Q charge over here and minus Q charge over here. And when we multiply by the electric field, we just write plus QE and minus QE. But the 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 field lines emanating from positive is in this direction, and this direction, minus Q, it is towards this. Okay, towards the other thing, because it gets attracted towards that. So that will be given a negative QE. Okay, so negative QE towards that position and plus QE from that position. And this causes, the electric field causes this effect. That means positive is tilted toward this and negative charge is tilted toward this position. So there is a tilt happening, and the distance between this is 2a. So by now we can tell what is a torque. Understand, when we sit in a chair, when we sit in a chair, it is not like an Avenger film. We just lay there and just stand like this. No, we will just sit and then turn and then be in the erect position. So that rotational effect, how can that rotational effect occur? We have muscles to overcome gravitation. Gravitational pull is pulling us downwards. Okay, that is the force like this, towards downwards. And we are taking our muscular strength to get against this gravitational position. So we cannot go like this way. Okay, we can't fly. We will just tilting our limbs like this. We will just hold like this and then somewhat move forward and get erect. That rotational effect is also called torque. So this thing now, dipole will also experience a torque when it is experiencing this electric field like we experiencing the gravitational field. Okay, so so every time when you get up a chair now, you just bend forward a little and then adjust yourself against that gravitation to be erect against the opposite direction by the help of your muscles and stay erect, and then start your walk or something. So that's the effect, the rotational effect due to two forces. You are in the earlier simple case I have said the muscular forces against the gravitation. That's the torque. Here, this dipole, that is against dipole character is against this electrical field. That makes the torque happen. So by the heading itself, torque on an electric dipole placed in a uniform electric field. How this become uniform? Because equal amount of charges are uniformly distributed. From that, equal amounts of field lines emerge and end at another point. That means uniform electric field dipole is placed. We know that all the variables nomenclature. Now, this is a negative charge A, positive. It is negative is A and positive is B. Plus charge plus minus Q charge and distance between 2A, and then electric field is this direction, and the angle made by this dipole with the field is theta. Angle made by the dipole with the electric field is theta. Thus, and I will name a triangle over here, ACB triangle. Okay, that means the triangle when it is taken over here, that means sine theta is equal to opposite side by hypotenuse. That means opposite side is BC length divided by this hypotenuse length is the length of the dipole 2a. Remember this, it will be useful in our further calculations. So I have explained the diagram well, and then comes a rotational effect on the dipole is equal to that is torque. The rotational effect due to the two forces, no, and the dipole force and the electrical field, which is the dipole character and the electric field is against each other. So rotational effect due to this dipole is equal to that is the torque, which is produced over there. Interaction of two forces, then there is a rotational effect. That's the torque is equal to magnitude of either force. If you will take either of the force, magnitude of either of the force into perpendicular distance between line of action of force. Okay, line of action, that means what here? There is a line of action. That means a rotation effect. No, there will be a line of action like this. Just we will make this thing now against this, a uniform field against that. Now we will take BC position. Okay, that means a magnitude of force. That means a Q into E is our Coulomb's force. No, that means E is equal to 1 by 4 pi epsilon 0 Q by R square, then Q into Q, that is the force, the Coulombic force. That Coulombic force into BC is what? Distance between line of action of forces. That means this action, and it will come, let it be placed here, and this will come over here. No, that line, how much you want to be in that line against that. Okay, it was placed like that, it want to be getting like this. So BC should be taken as the line of action of these forces of the electric field, and then this dipole should be in the vertical position. So just equating into a what we all know, torque is equal to QE, that is the Coulombic force into the distance between line of action of forces. So this BC now is equal to, I have said earlier, sine theta into 2a. So 2a sine theta, I have written over here. Tau is equal to Q into 2a into E. I have rearranged Q into 2a, E into sine theta. So Q into 2a now is the dipole moment. You know earlier, dipole moment P is equal to Q into 2a, the charge into the distance between the dipoles. Okay, two poles. So P into E sine theta. That's the torque. Okay, but this P E sine theta, whenever you see now P into E into sine theta, then just we can write in another form also, the vector form. Vector contains two products, that is dot product and cross product. Here, if you see a sine theta, just put a cross. Sine for cross, sine for cross, sine for cross. And then direction of torque is perpendicular to plane containing this dipole moment and electric field density. That means that this direction of torque is perpendicular to the plane containing. What is the plane containing? E. This plane and this dipole. The direction of the torque will be perpendicular to the plane containing P and D. That means, okay, perpendicular to the plane. That means torque direction will be perpendicular to the plane containing this dipole moment and the electric field intensity. That's the essence you want to study. If you solve a problem, it will get very clear. By now you understand the whole thing, torque on a dipole placed in a uniform electric field. Rest, work done in rotating an electric dipole in a uniform electric field. That means a work should be done in rotating this electric dipole in a uniform electric field. A work should be done so as to move this. So work is the capacity to do the expenditure of energy, and movement. Work is equal to force per time. That's the thing. So this work done in rotating, the work which is done in rotating the electric dipole in a uniform electric field, we should calculate that. So first of all, I will explain this diagram and tell what is needed. This is a dipole, negative, positive. Okay, first position, we will take a field direction, uniform electric field direction E. Okay, let it be like this. Then the first angle it has is theta 1. Okay, then it will tilt to perpendicularly, it will tilt to an angle, what? This thing, theta 2 angle. Okay, That means a work should be done to bring theta 2 to theta 1 or theta 1 to theta 2. A work should be done. Understand that. That's it. So we will explain it in a way. Consider an electric dipole of a charge q. Okay, charge q is there, plus and negative, and a length 2a placed in a uniform electric field of intensity E at an angle theta with a direction of the field. Okay, theta 1 with the direction of field. Torque acting on the dipole, tau is equal to, P sine theta. What is it? That's the torque. Torque acting in this. We know the dipole moment, that is 2a, the distance, and q. That is enough. And E is the electric field given. And sine theta, we have the angle. So torque acting on the dipole is tau is equal to P sine theta. Let the dipole be turned through a small angle d theta. After that theta, just it is moving somewhat greater. A small angle d theta, which is over here. So at that point, the force into displacement, that force, the work, okay, I have said earlier a mistake, force per time or something. No, it is not that. The work, the force, into the distance. Force into distance. That means the work done. Then here the work done can be the distance. What is this angular distance here? This angle, first is angle. Next angle is traversed. Okay, that traversing angle is the displacement or the distance. Okay, so the force into distance or displacement is equal to the work done. So the work done is equal to small change in work done is equal to a change which occurs in a small angle. That is equated like this. So next comes the work done is equal to P sine theta into d theta. Okay, what is this? For tau, we have substituted P sine theta. And then the total work done in rotating dipole from theta to theta 1 to theta 2 is, that means the final value we can take here. That means P sine theta integral value. This is the upper limit and this is the lower limit. So we will take from theta 1 to theta 2. This is the thing. Upper limit and lower limit. Theta 1 to theta 2, putting an integral. P sine theta, then PE. What is integral of sine theta? We want to by heart it. Minus cos theta is the integral of sine theta. So minus cos theta we will write. Theta 1 and theta 2 is there. So putting the minus theta 1 minus theta cos theta 2. So minus cos theta will become like this. W is equal to the dipole moment into this electrical field intensity into cos theta 1 minus cos theta 2. That's the formula which we want to study. Okay, the first angle minus the second angle. That's the work done. Okay, and then we will turn about in the physical significance of the dipole. That means dipole is it's a material. It is consisting of the molecules of dielectric also. Dielectric means there will be positive and negative charged polar molecules and non-polar molecules. That is, I will tell in a way that the physical significance of dipole. That is the heading, and in which it is described the molecules of dielectric is classified into two classes. Two classes are there, of which dielectrics are constituted, which is the polar molecules and non-polar molecules. The polar molecules is having the centers of positive and negative charge. No, they do not coincide. Okay, that they are placed away from each other. H plus and Cl minus placed away from each other. H2 and O is placed away from each other. They do not coincide. The centers of positive and negative charges never coincide. That is polar molecules. They have a permanent dipole moment. Okay, they have a permanent dipole moment. Example, water and HCl. Next is the dielectrics, non-polar molecular dielectrics. Those centers of positive and negative charges coincide and they have no permanent dipole moment. Example, carbon dioxide and methane. Okay, remember that. Polar and non-polar molecules are included in the dielectrics, which is included in the significance of dipole. Okay, I will come with the practical usage of these equations and further board examination questions. Even if I put all the good content in, please support me, like, share, and subscribe my channel. Tell your parents also. So be cool, be happy. Bye.